Hi everybody, my name is Una, and as part of my master's research project, I'll be presenting how to use noisy data to make long-term predictions and select the right patient. Throughout this presentation, I'll be covering three key questions, and these are: what are the sources of noise in high throughput data? What are the useful strategies for tackling this noise? And can you generate reproducible predictive markers across clinical studies? Gene expression data has been used to create gene signatures for decades now, signatures capable of predicting things, for example, tumor growth or cancer behavior in the future. Two notable examples of this have been in 2002, where a 70 gene set was created, and in 2005, where a 76 gene set was created. Both of these predicted for the exact same thing, which was whether a breast cancer tumor was predicted to metastasize in the distant future. Both of them had high predictive performance for their own data sets, and both were published in reputable journals. However, a couple years down the line, some analysis was done on these signatures, and an interesting problem was brought to light, which was if you consider both of them, they actually only have 3 genes in common, even though they predict for the exact same thing. And this essentially highlights the reproducibility problem that comes along with these specifically correlation-based signatures. Gene expression data is inherently noisy, and majority of this noise is cohort-specific. So if you just pick the genes that correlate with your outcome, you tend to pick out noise that is specific to your particular dataset, and that is what is determining your signature. If you change the dataset, you get a different signature. And equally so, if you use your signature to predict on a different dataset, the predictive performance of your signature will be significantly worse. Now, this brings us to the question of where does this noise come from? So, gene expression data is extremely sensitive to so many different sources. So, the range of where the noise actually comes from is massive. But it's all the way from seemingly unimportant things like circadian rhythm or environmental factors like metabolism, nutrient availability, stress of the individual getting measured, or even things just like measurement bias. And interestingly enough, a study conducted in 2011 actually found that the average gene signature is not significantly better at predicting its own outcome than another random signature of equal size, and I feel like this is the perfect example of just how deeply rooted this noise issue is within gene expression data. Which leads to the question of my project, which is how do we create a gene signature that is able to overcome this noise to predict specifically continuous tumor growth rate? And the method that we propose for this is to combine two existing processes called RWR, or random walk with restart, and LASSO regression. So genes sit in a network and they are connected by something called edges. Every single gene has its own gene expression, and this is where that noise lives, if you will. So what RWR does is it spreads this expression over the network. It shares one gene's expression to its neighbors, and the amount that it shares by is determined by the strength of the edges, or here depicted by the thickness of the arrow, the W, like so. And what you are left with is a smoothed network where the random noise gets distributed while the important true signal still stays. So that was random walk with restart, and the second part is LASSO regression. Obviously, this is much better than what we had at the start. However, there's still a lot of genes present, and what we ideally want is a short and interpretable signature. So every gene also has something called a gene weight, which is basically a value describing how much that gene contributes towards a particular outcome. Now, what LASSO does is it imposes something called an L1 penalty onto these gene weights, essentially pushing them towards 0. And what that means for small weights is that they get pushed to 0. And if you think back to the definition of what the weights are, it means that they contribute nothing towards your outcome. Essentially, they are removed from the signature. So what we are left with is a short and interpretable signature where all of the genes are important and independent, and only these are present. And that's exactly what you want when you have significantly more genes present in your data than tumors, and therefore dimensionality is an issue. So in this proposed concept, if you really think about it, there's kind of two opposing things going on. RWR adds a layer of complexity into your final signature by incorporating the full network structure. However, LASSO adds a layer of simplicity to it by stripping down the signature to a minimum where only the important and independent genes are remaining. Which leads directly to the hypothesis of this project, which is that striking the balance between this biological complexity and the model simplicity can be used to predict continuous tumor growth rate. For this project, we have been using the Novartis 2015 patient-derived xenograft trial data, specifically extracting the continuous tumor growth rates from that and also the gene expression data. Now, in terms of the edges that I mentioned earlier, what we've been using is the Pathway Commons dataset, specifically filtered to the hallmarks of cancer genes and the genes present in our dataset, and we get the edges from that, and all of those things get input into our algorithm. So in order to be able to discuss the very preliminary results that we have at this point, we have to consider this equation, which is the objective function. So if you remember earlier, I was discussing the LASSO regression and the L1 penalty that it imposes. That penalty is made up of two parameters, which are lambda and beta. So what lambda does is it basically is a measure of the complexity or the sparsity of your final signature. If lambda is higher, more of these weights get pushed towards 0. Now, beta, on the other hand, is basically, it decides the balance between how much of that lambda is pushed towards the edges versus how much of it is pushed towards the genes. So what we did is we took all of the colorectal cancer sample data from the Novartis dataset, we trained our algorithm on these, and then we used the output gene and edge weights to basically refit the data and calculate the predicted tumor growth rates from this fit. And here you could see the results from that. We essentially had 43 tumors to work with around 1,600 genes and around 90,000 edges. And as you could see, the fit was essentially 1-to-1. However, I do have to note that this is a fit, not a validation. So as mentioned, these results are very preliminary at this stage. Now, thinking back to these lambda and beta values, for these results, we set arbitrary lambda value of 0.001 and beta of 0. Now, if we plug this back into that equation from earlier, what we find is that this combination of lambda and beta values means that there is no L1 penalty imposed on the edges, and there is a penalty imposed on the genes. And you can see that right here, where about 800 of those genes had their gene weights pushed to 0. Now, what we would ideally want is even more of those weights pushed towards 0 to make our signature even more sparse. However, that will come with further tuning these parameters. And here you can also see that out of the edge weights, none of them were pushed towards 0, so all of them had either positive or negative values. So for the next steps, the most obvious and important one would be to tune these hyperparameters, so the lambda, the beta, and something called alpha, which is the restart probability of random walk with restart. Now, another thing is the data itself. If you remember, I said we had 43 tumors, around 1,600 genes, and 90,000 edges. So the dimensionality of that data is massive. So we might need to consider a data set either with more tumors present or just using different tumor types from that Novartis dataset. Another thing is the gene expression normalization. So as of right now, we've been using Z-score normalization for the gene expression data, which means that some of those values will be negative after normalization. Now, that isn't something that is ever done for RWR, so we need to look at how the RWR actually works with that and whether it does. And I think the most important is once we have our final model fit, to assess the biological relevance of those finally selected edge and gene weights. because that leads to reproducibility in other datasets too. Which leads us to answering the last question I posed at the start. Can we generate reproducible predictive markers across clinical studies? Referring to this problem. And the answer is partially. So on the same two cohort datasets that I had mentioned on the first slide, considering subnetworks rather than individual genes actually increased that overlap, which was 3 genes before, from that 1% to about 13%. Now, although I'm aware that 13% is not a massive number, it's still a tenfold increase, and that increase shows that considering networks is definitely a step in the right direction, and we believe that we might be able to push that percentage even higher with our approach. So thank you so much for listening. I hope you enjoyed.